Hey everybody, welcome back to chemistry. And now we have gotten to a very important point in chemistry. What I'm going to do right now is talk about what valence electrons are. Valence electrons are the electrons in the atom that really determine the atom's properties. And so you really have to understand what they are. Also, at the same time, what I'm going to be doing is talking about core electrons. And so at this point, you kind of know when you're looking at an atom that not all of the electrons are exactly the same distance away from the nucleus. You know that some are very close to the nucleus, some are a little bit further away, and some are very far away from the nucleus. And so what the valence electrons are the electrons that are the furthest away from the nucleus. The valence electrons are the ones that are counted in the highest energy level only. They're in the highest shell. So the reason why those electrons so far away are so important in determining an atom's properties is it's because those electrons that are furthest away from the nucleus tend to be very loosely held. And it's there where other atoms will get close to that atom with the valence electrons and bind with that atom, and will bind with that atom through that atom's valence electrons. Now, all the other electrons in the atom that are not valence electrons, that are further in and close to the nucleus, those are the core electrons. And the core electrons, because they are not on the outside of the atom, those core electrons tend to not interact with other atoms. And so what I want to do now is I want you to get used to being able to determine what the valence electrons of an atom are and to count them. So I'm going to bring up this slide here. And so why don't we go ahead and increase the size of the slide. And so here what we're doing is we are looking at a chlorine atom. And so the atomic number of chlorine as indicated by Z is 17. If it's a neutral atom, it has 17 electrons. And here what you can see is I've written out chlorine's electron configuration. So you should be able to look at this electron configuration and identify which ones are the valence electrons. And so here I kind of pointed out here that the valence electrons here are the ones that are in chlorine's highest energy level. So one thing I want you to notice in chlorine's configuration, there is a first energy level of 2 electrons. There is a second energy level with 8 electrons. The third energy level, there are 2 in the S sublevel and 5 in the P sublevel. So really there are a total of 7 valence electrons in chlorine. So you should be able to look at a configuration like this and count the valence electrons. Now all the other electrons that we did not count as valence electrons are core electrons. Okay, so let's look at it in a different way. Another way you can write out chlorine's configuration is with this abbreviated configuration. So you might remember that here that chlorine can be represented as neon's 10 electrons and then adding 7 more to it in the highest energy level. Well, now you can sort of see is that the core electrons in an atom will be usually the same as the noble gas number of electrons in the abbreviated configuration. And then the valence electrons are going to be the ones that are kind of written out in the individual sublevels. Okay, so let's do another one. Let's figure out the number of valence electrons in calcium. And so what do? So there's calcium, its atomic number is 20 here. And so here is its configuration, and I'm hoping you'll be able to write that out. And what you'll see is that there's a first energy level, a second, a third, and a fourth. And you can identify that the fourth energy level is the numerically highest energy level, and there are 2 electrons in it. So in calcium, there are 2 valence electrons, and then the rest of the electrons here in calcium that are deeper in the atom, which are closer to the nucleus in the first, second, and third energy levels, so there's a total of 18 there. those are the core electrons. There is another way of writing out calcium's configuration. And again, you can sort of see is that here the core electrons, the 18 of them, are argon's configuration. But to get out to calcium's configuration, you have to add 2 more electrons, which will be further out, and those will be the valence electrons. Okay, so this is a very important thing to be able to do, and so let me show you why. And so this slide asks, why do elements in the same column have similar properties? And the reason is because they have the same number of outer valence electrons. So let me kind of explain this with the example of the next to last column in the periodic table. So this is the next to last column here in the periodic table. This is the halogens, and so here in period 2 is fluorine here. Its atomic number is 9. And then below that is chlorine. Its atomic number is 17. Bromine, atomic number 35. And iodine, atomic number of 53. So what you can do is you can write out the electron configurations for each of these atoms. And so let's look at the electron configuration for fluorine. Fluorine has 9 electrons. Here's its configuration. And I'm hoping what you can see is it has, as its outermost electrons, 2 electrons in the S sublevel of the second energy level and 5 electrons in the P sublevel of the second energy level. So it really has a total of 7 valence electrons. If you go down 1 element here in the periodic table, guess what? Now we're at chlorine, which has a lot more electrons. It has 17 electrons. And so by the time you get to chlorine here, the first and second energy level is filled with electrons. And so those will be part of a neon's configuration. But then chlorine is more. It's 7 more electrons than neon. And guess what? Those will be further out, but now they're in the 3rd energy level. But here's the thing. Chlorine has the same number of valence electrons as fluorine. It's just that they're further out. They're in the 3rd energy level, while fluorine's valence electrons are in the 2nd energy level. So you can continue on with this. Here is bromine's configuration here. And so it has 35 electrons. And then the electrons that are furthest out in bromine are going to be here in the 4th energy level. So we have 2 and 4s, and we have 5 and 4p. So it really also has 7 valence electrons. And similar argument with iodine here. If you look carefully at its structure, its highest energy level, which is the 5th, it also has 7 valence electrons. And so all of these elements have 7 valence electrons. So if I can reduce the slide for a second here, I want to sort of talk about why these elements kind of have similar properties. And so what we like to do in chemistry is we like to sort of come up with a notation that really emphasizes the number of valence electrons an atom has. And so it's called electron dot notation. So here is good old fluorine. And so we figured out it has 7 valence electrons. And so we indicate this with 7 dots like this. I'll talk more about how to do the dots in a bit. But there's fluorine's configuration. Guess what? Chlorine also has 7 valence electrons, and so it has 7 dots. But here, while with fluorine, those valence electrons here, those dots are in the 2nd energy level. Of chlorine, they're going to be in an energy level that's further out. It's going to be the 3rd energy level. And so bromine also has 7 valence electrons, and it has 7 dots. And same thing with iodine. And so with iodine, I'm hoping you can sort of imagine here that these electrons, these valence electrons, these 7 are in the 5th energy level. Okay, so why is it that these elements have similar properties? And the reason is because they have the same number of outermost electrons. There are 7 electrons that can interact with other atoms. And so here, these elements with the same number of outer electrons will probably interact the same way with other elements. Let me just give you a quick example. So if you look at compounds of sodium with each of these elements here, what you'll see, for example, With fluorine, it'll be sodium fluoride. So it's one atom of sodium bound to one atom of fluorine. You will never see this. You will never see two atoms of sodium bound to one atom of fluorine, nor will you see one atom of sodium bound to two atoms of fluorine, and so on. You never see this. It's always one atom of sodium and one atom of fluorine. Well, guess what? If you can imagine that one atom of sodium will bind to fluorine, you can well predict that one atom of sodium will also bind to one atom of chlorine and bromine and iodine. So here we have, you're going to have sodium chloride like this, one atom of sodium and one atom of chlorine, and never Na2Cl or NaCl2, or it's going to be NaBr, one atom sodium, one atom bromine, or NaI. That's always the case. So the question is, why is it that one atom of sodium will bind with one atom of these halogens? And the reason is this. You'll see in a minute that sodium, because it's in group 1, it's an alkali metal, only has one valence electron. Here will represent the valence electron as an X. Now what you're going to learn is that sodium and fluorine will stick together. And what will happen is this. You'll have sodium here and you'll have fluorine. So let me write out fluorine's 7 valence electrons like this. And then sodium binds to it merely by giving its electron to fluorine. You'll learn later when that happens, fluorine gets a negative charge and sodium gets a positive charge. So can you see why one atom of sodium only binds with one atom of the other elements? It's the same deal. Sodium here gives up its one electron to the other halogens, which have 7 valence electrons. And so also it's going to happen when it combines with bromine. You will get this, and the same thing will happen when you get iodine combining with sodium. So it's always one atom of sodium with one atom of halogen. So I'm hoping this re-emphasizes here that when you have a column of elements, they should have the same number of valence electrons. In the case of the halogens, it's 7, and they'll have similar properties. In this case, they're binding with just one atom of sodium, say, not 2 or 3. Okay, so if I can increase the slide again, here I have an additional slide that sort of talks a little bit about this in more detail, and I encourage you to look at that. At this point, what I want to do is bring up a periodic table and show you how you can quickly determine the number of valence electrons in an atom. So one way to do it is to here say with boron, what you can do is figure out its electron configuration. So let me quickly figure that out. It is 1s2, 2s2, 2p1. And so what I'm hoping you can see is that boron, because it has 3 electrons in the second energy level, has 3 valence electrons. But there's actually another way you can do it oftentimes. The way you can do it is if the element is in the main group elements, in other words, the element is either part of the S block or the P block here, you can rapidly determine the number of valence electrons by its location. So in the first column, all elements here in the first column have 1 valence electron. So I'm going to symbolize the symbol of the element as X, and I'm going to put a dot, a single dot here to indicate all the alkali metals here and hydrogen have 1 valence electron. Here in the second column, what we have here is we have all elements having 2 valence electrons. And so what you can do is you can put 1 dot here, and then if you want to, you can put a dot on the other side. Now, what we do is we skip the transition elements here. We probably will not be determining the number of valence electrons in the transition elements. And now we go into the P block. And so here we're in group 13. And in fact, in older periodic tables, this is considered to be group 3A. So let me just indicate here in some of the older periodic tables, it's called 3A. And so guess what? How many valence electrons these elements have? And so they have 3 valence electrons. So I'm going to represent this with 3 dots like that. The next column over is group 4A. And so you have 4 valence electrons. for these elements. So as a quick example, if you look at carbon and silicon, germanium, they will have 4 valence electrons, 4 electrons in their highest energy levels, and they look like that. And so nitrogen in group 5A, for example, has 5 valence electrons, and so when you get to 5, you have to start pairing up dots like that. So, and then 3 more like this, and then when we get to 6A, which oxygen is a part of, here it's going to be 6 dots like this. Start pairing them up. I'm doing the best I can drawing this. It's a little tricky here. Okay, and then 7A here, fluorine, chlorine, bromine, iodine. Those are the halogens. And so here is the elemental symbol X. And so it has 7 dots. Now the noble gases are a little bit tricky. So if you're below helium and you go neon on down here, these noble gases have 8 valence electrons because they're in group 8A or 18. But the thing you have to remember is helium is different. And helium is different because helium only has 2 electrons. So it cannot possibly have 8 valence electrons. So helium looks like this. And it has 2 dots like this. 1, 2. Let's finish up with a final practice question. Can you draw out a correct electron dot symbol structure for the element germanium? So you have to remember that germanium, its symbol is Ge. Its atomic number is 32 here. And so what I'm hoping that you see is that it's a part of group 14. In the old periodic tables, it's 4A. And so if it is part of group 14, subtract 10, and that tells you that it has 4 valence electrons. So germanium looked like this. Okay, well, thank you for listening to that, and we'll see you next time.